Hello. Hello, can you hear me?
Yes, ma'am, you are audible.
You can all see my screen, right?
Yes, ma'am.
Okay, um, so this week's content primarily covers object detection and segmentation, right? Like I'll go over the trajectory of how object detection algorithms evolved and briefly look into the segmentation ones and then some notebooks. Yeah, so like these are some classical computer vision tasks, right? So in a classification task, what we try to do is, given an image, we try to associate a label with it, right? Like in this case, that this picture has a cat, so we have one label for an image. In the case of yeah, but sometimes we might want to exactly localize where an object is present, right? So what is an application where you would need object detection? Any one of you? Any examples? So object detection or classification plus localization is done where not just like if uh, what is there in the image and you also want to localize where exactly a particular object is present, right? Like how you see in the third case. So there's a dog, there's a cat, and there's a duck here, and you have a bounding box associated with each of them. So which says I have cat in this particular region, dog in this particular region, duck in this particular region in an image. So that is what is referred to as object detection. So what is an application which where this is very useful or needed? On roads, yeah, it's required in like autonomous vehicles, right? To track where the road starts, I mean, like if there are any pedestrians moving, to track them, such things. Or even in traffic monitoring and things, like to track locate where license plates are there, such tasks, right? And yeah, another mm, well-known problem is segmentation. So in segmentation, what we do is we associate a label for each pixel in the image, not just a box, but exactly where an object is present, right? Like in this region, as you can see, like this region is where a dog is present, and every pixel inside this will be labeled as dog, and every pixel in this we expect it to predict as cat. So how many predictions will we, so suppose this is a 100 cross 100 image, how many predictions will we get for in the case of segmentation? See, in classification we get one output, right? That it's a cat. So in the second case, in where there's one object, classification plus localization, how many outputs will we get here? Anyone? So what is that extra information I'm predicting here? Two. Okay, what are the two? yeah, two in the sense one location and classification, right? So by location, what exactly do we mean? So I'm asking how many numbers should we predict, like how many elements, coordinates, right? So a location usually what we need 4 coordinates, right? Or so it can either be done as center and width and height. So you have xy for the center and width and height, 4 coordinates, or this corner and width and height. So you need 4 numbers to predict a box and classification. So in total 5 outputs are required here, right? And what about general object detection? So do we know how many predictions we get? Not really, right? So the number of final predictions we'll get is number of object expected. This is number of objects into 5. That is 4 plus 1, right? 4 for the coordinates, the bounding box location, and 1 for the class name, which class. So this is, so if there are like 5 objects, then I expect 5 into 5 predictions to come out. But the number of real objects present in the image versus what gets predicted might not always be the same. Some object might not be detected. We'll see how we'll design a loss and all for this task. So in that sense, if I have instance segmentation, how many predictions will I get for if I give an image? So how many numbers should I get as my final output if it's a 100 cross 100 image? So how many predictions should I get for segmentation? How many numbers if there are 100 cross 100? By looking at this example, for every pixel I want to make a prediction, right? For all these dog pixels I want to predict dog, for cat pixels this, for these ones. So the if there is no object, then these are usually what we expect to get predicted as background. This is background. Number of classes. So suppose say it's a 3 class, I need 3 classes here. 10 to the power 4, 10 to the power 4, yeah, it is 10 to the power 4 here. So basically it is number of, yeah, in this case 10 to the power 4, because for each pixel I get one class prediction, right? So it is number of pixels in the image, yeah, the basically number of pixels in the image, and at each pixel I predict pixel, I get one class prediction. So the final output is 100 cross 100. So this is how I think RCNN first came out in 2013, I think. I'm not exactly sure. Yeah, I think it's 2013. So this is how the object detection frameworks evolved. So the first one is called so the first one, RCNN, is called region proposal convolutional neural network, and then a fast version of that came out. Then a faster version of that, and then so these 3 of them are actually two-stage frameworks, and then there came out so many variants of YOLO and SSD, which are our single stage frameworks. So when I say 2 stages, so in an object detection, what could the 2 stages refer to? Any guess? So what is the task? We have two things, right? One is to detect the boxes where an object can be present. Detection and location. Both are the same, right? Detection and classification, more like. So the two stages will refer to detection of bounding boxes and then classification of what object is present in the bounding box. So they approach it in these two stages where in the first stage you just get a possible number of bounding boxes where an object could be present. In the second stage you perform classification of the objects present in each of the bounding box. And then in this later frameworks like YOLO and SST, they combined both the stages and which predicts both the bounding boxes and which classes in one shot. As in passing once through a network, you give an image and you get all this as outputs. There are no two stages involved. So RCNN has two stages in it. The first one is the region proposal stage and the second one is the object detection stage. So region proposal stage basically takes in an input image and it does something called the selective search algorithm, and it gives out a lot of possible prediction like bounding box locations. So it would basically give out a lot of these patches extracted from the image saying possibly an object exists in this image. So why is this proposal stage required? So in an image, how many such boxes can I come up with? Pretty huge, right? Like I can have really small boxes to huge boxes. If I have to span the whole of the image grid, I would have a really big number of boxes, but I need to reduce that search space, right? And based on some heuristics, so they use something called like predict some blobs in the image and then combine them and something like that, and selective search gives out region proposals, so where all an image could exist. So basically we can crop out all these proposals which are given by selective search, and so these are regions proposed. So it gives out like 2000 region proposals. Even that is a lot, right? In general we don't really have like 2000 objects in an image. So once but still that is much lesser than what is possible in the given image, right? So these region proposals are then affine warped. That means so each of these patch could be of different size, right? Like so this could be say 20 cross 20 pixels and this could be 20 cross 30 pixels. So each patch could be of different shape, but then in the later stage I want to pass it through a CNN, for which I want a fixed dimensional image. So they do this affine warping where all of this is resides to a fixed dimension. So if it's 22 cross 20, it will be upsampled to get 227 cross 227, which is the input dimension for this AlexNet VGG kind of architecture. So all of this is resized. So by resizing, the aspect ratio can get screwed up, right? Will be affected, but that's fine. So we get these warp proposals which are then passed through a CNN. So in the last week's class we discussed all these architectures, right? Like AlexNet, VGGNet and so on. So what object detectors usually do is they take the pre-trained ImageNet, that is the convolutional neural network part, and get the feature maps from it. So they ignore the last fully connected layer. So usually it's that ImageNet layer. So I would have a CNN followed by an FC layer, which would be that 1000 class classifier, right? Yeah, which was trained on ImageNet. So they don't take this fully connected layer, they only take the pre-trained CNN, which is trained on ImageNet. Trained on ImageNet, they take this CNN, get the feature maps output. So this will be spatial, right? I don't know, I think it's like 4 cross 4 cross some 128 channels or something like that it would be. So these feature maps are then passed through a fully connected layer, which does the classification for each box. So we have these region proposals, and then we pass this feature map through based on whatever the number of, say I have 10 objects, so it is passed through a fully connected network and then passed through a softmax layer to get 10 class predictions, which of the 10 classes this particular object belongs to types. And they use these features as also train class specific SVMs. This is like an auxiliary objective used to train the features. So the same feature maps are also passed through another different fully connected layer to do bounding box regression. So bounding box regression, what it does is it predicts like the delta x, delta y, delta w, delta h for these boxes. So suppose there is a box which is, so there's a proposal which looked, say, just this part of the image, doesn't contain the whole object. In such cases, it is trained to predict how much the proposal should have been shifted so that it matches with my ground truth bounding box. So this is trained to predict this bounding box offset. So basically at the end so this is the loss for localization, and these two objectives are towards the task of classification. So while testing, what would be done is a new image would come, pass it through selective search, get these proposals. For each of these proposal, I get these predictions. It would basically follow this path, and I would get a prediction for each box. But then there are 2000 proposals, right? 2000 proposals. Obviously, all 2000 of them would not have objects. It's just forcing and predicting this. So which is so we basically have to filter out those 2000 boxes and then identify what are the true like where are the objects present truly. So that is usually done by something called non-maximal suppression. Where it is non-maximal suppression? Yeah, so this non-maximal suppression is an algorithm used in all object detection algorithm. I mean, that's RCNN, faster RCNN, because all of them would give out like a huge number of boxes which I need to filter out. So what this does is, say there were, so like suppose my this is what my object is where my object is present. There would be multiple boxes which would be spanning this object, right? So I don't need those redundant boxes. I could just remove one of them based on how much it intersects with. So suppose there were two proposals here, the red one, B1, the box B1 and B2 also. So what is done here in MS is that you take one of these boxes, say B1, and I'll see what are all the other boxes it interferes with, compute this intersection over union. So intersection over union is the the numerator of the IOU is basically intersection area of these two bounding boxes, right, which is this blue region you see here. So the area of this divided by the union area, which is the area occupied by both the bounding boxes put together. So I do this, and then they put a threshold over this IOU. Like if this IOU is greater than some point 0.7 or something like that, that means that they are highly overlapping, right? This captures to what extent two boxes overlap. So if they overlap, yeah, if IOU is greater than, I think 0.5 is like standardly used. If the IOU threshold, I mean, if this IOU is greater than 0.5, then I remove B2. I don't consider B2 because both of them span the same region. So yeah, when we have such multiple boxes here where all of them predict the same object to be present, so I select one box. Say I select this one particular box here. I select one of them, and I will then check its IOU with each of the other boxes. Because all of them highly overlap here, I reject all of them, remove them from this list. Yeah, and so when I take this box and intersection with these, obviously they don't intersect, so it doesn't matter. Only if this is redundant, then we remove this by doing non-maximal suppression. So we're removing the redundant boxes, and we get this as the final predictions. So in all RCNN, if faster RCNN, SSD, YOLO, in all of them, this non-maximal suppression is one common thing. Um, any doubts on this NMS? So this is usually done in testing stage. So we looked at the RCNN framework now, right? So by looking at this framework, can you tell um, which parts of this can be computationally expensive, and where is there any scope of modifying this algorithm to make it faster? Like why is this algorithm slow? So to just like get an idea, it would used to take about like I think 40 to 50 seconds per image to get bounding box predictions using RCNN, which is a lot, right? So which aspect of this whole framework is the most expensive part computationally and with time, obviously? Oh, selective search. Why selective search? Yeah, I mean, I understand selective search. Selective search is one place to be improved upon, definitely. But suppose I'm still dealing with multi-stage frameworks where I have region proposal stage and the second part. Um, it is still done only once on the image, right? I give an image, class-wise SVMs. Class-wise SVMs are not all. They are all not computationally expensive. They're just single one small layers, right? Not in terms of the network. Why would this thing be time consuming? CNN, all the frameworks have CNNs, so not. So that is common. I can't avoid that. I still need to use CNNs. So the computation have to scan multiple regions in an image. Yes, yes, right. Yes, that is the most expensive part. So given 2000 region proposals, here, yeah, here all 2000 region proposals I work them and pass all 2000 images through the CNN, right? Which is what makes this whole framework computationally expensive. That's like I'm doing 2000 forward passes and backward passes during training. For each image, I'm doing so much computation, which is very expensive. So, can we get rid of this part? Like, why should I pass every single region to the CNN? So, there is so much overlap in information, right? Because I have 2000 bounding boxes predicted, and so many of them actually overlap. Like, when you see here, uh, like if this is how all our bounding box proposals are, and I'm passing each of this box through the CNN, which is pretty much containing like there's so much redundant information which I'm passing through the CNN. It's not required. So can we avoid that part? Like, can we mitigate passing these 2000 proposals individually to the CNN? So that is what is addressed in fast CNN. So they get rid of that redundant part. So what they do is, so they still have the selective search algorithm to propose the regions, but then instead of passing each of the region to the CNN, what they do is they pass the whole image to the pre-trained CNN. We get the feature maps, and based on where the regions are present, I mean these proposals are, we get these bounding boxes, right? X, Y, W, H. So based on where these are, from the feature maps, those features are extracted, right? So there's one object here, right? The lady sitting here. So that would correspond to this region in my feature map. So they extract these feature maps for each of these object. So this is a one-time process. So if I have one image, I'm passing it only once, rather than 2000 forward passes. And from this feature maps, I extract these feature maps, and then I further do the classification, regression, all that part on these feature maps. But this part is the redundancy here is gotten rid of, right? So they have this layer called ROI pooling layer, which is again so in this case we had this warping part, right? Because CNN takes in a fixed size input. So whatever the input crop is, I'll warp it to the same size and pass it through the CNN. So here also these feature maps, each of them will be of different dimension, right? But I don't want those different dimensions. So this is basically ROI pooling layer is like warping done on the feature maps, so that the next so it becomes scale invariant, as in all of them are of the same shape, which I pass it for the later fully connected networks. So how does this ROI pooling layer work? So now suppose this FC network, so I've designed so that it takes in 4x4, I mean 2x2 input. So whatever, so this feature map could be of size 2, and this could be of dimension say 2x6. But I have to warp it to 2x2. So whatever the input size is, I should warp it to 2x2. So what is done here is, so whatever this feature map dimension is, so we make it into blocks of 2x2. That is, so I take this, so I divide the width of this feature map by 2, so it's like 1 pixel. But along the height, if I divide by 2, it takes in basically 3 pixels, right? Like 3 elements in this feature map. And then each of this is pulled to get one output here. Like usually max pooling is done. So out of these 3 values, yeah, these 3, it goes here. What is the question? What if the feature map dimension is less than 2x2? If it is 1x2, if it is 1x2, then you can repeat that 1x2. Like if it is 1x2, I can copy the same elements, whatever is here. If I have AAB, can do AAB and then AAB here. if it is bigger, then I pull them and get it, like pick them, right? So irrespective of what your feature map like crop is, you do h by I mean width by 2, height by 2, and each block in that is mapped to one element in this. So this is called as what ROI pooling. ROI means regions of interest. Regions of interest pooling. So there is, and so ROI pooling, it does not have any weights, right? It's just pooling operation. So there it has no weights. We still call all of these as layers, but layers doesn't mean they have weights. So now what do we have? So we have the image, and say 2000 proposals have 2000, okay, 2000 bounding box proposals, which I have passed through this ROI pooling, and I have got this feature maps, right? So 2000, if each feature map dimension could be 2 cross 2 into channel dimension, something like 128 or something like that. So then I pass this through two fully connected layers. One fully connected layer which handles the classification, another fully connected layer which does the bounding box regression. So for classification is cross entropy loss. For bounding box regression there is something called smooth. The smooth L1 loss looks something like this. In the region like -1 to 1, it follows like x square rule, and after that it's linear. This is x, this is x, then this is -x line. So bounding box regression is basically like learning this offsets for, like I have center w and h. So bounding box regression layers usually predict delta x, delta y, delta w, delta h. So I'll have ground truth bounding boxes, and then this would predict some bounding boxes. Yeah, so it predicts the difference, how much the proposal should be shifted so that it matches a ground truth bounding box. So this part is pretty much common across frameworks, just that how you handle the bounding how you obtain this bounding box and pass to the network, this part is usually changed and made more efficient. But all the models require these two elements, right? One FC layer to handle classification, one FC layer to handle bounding box regression. So fine, like one major element which was time consuming, which we got rid of while going from RCNN to fast RCNN. So now we know that there's another better model, right, which came out after fast RCNN, which they called as faster RCNN. So which part do you think they addressed in faster RCNN? Even this is still a two-stage framework. So what is the other expensive part which we still have? The selective search, yes. So the selective search. So why do we need? So what the thought was, why do we need to do this separately? Why can't we just use a CNN to do even the region proposals? So anyway, I'm passing the input image, getting the CNN features till here, right? So why can't I use the CNN features, which are actually very informative, to identify where an object could be possibly present? So what they do is they get the feature maps and then use this feature maps to predict the bounding boxes rather than a heuristic way of doing selective search on the pixels directly. So that's what they do here. We have an image, pass it through a CNN, we obtain the feature maps. From the feature maps, all the feature maps are passed to a region proposal network. So this is another CNN. I mean, like CNN or fully connected layers, all of them will be there. So this gives out our bounding box proposals. So we don't have selective search. So this gives out bounding box proposals, and those and this part is exactly the same as what is done in the previous step, right? So once you have the bounding boxes, you do that ROI pooling. We take the feature maps, we take the bounding boxes, do ROI pooling, then we do the classification. One part is classification and another one is uh, bounding box regression. Uh, so how exactly this RPN network works is that um, so when I say bounding box proposals, so I need to give out possible locations of XYWH, right? And there could be any number of such locations. So for this, what they do is they introduce something called as anchor boxes. That is, if I have an image, so they predefine certain number of boxes. That is like at every location they would say I will consider a few boxes, possibly something like this, with different aspect ratios. So a fixed number of bounding boxes. So you could take like say around 10 cross 10 locations in the image, and at each location I define some five anchor boxes like this. And so this region proposal network gives out these many boxes, and for each box we expect it to say whether an object is present in that or not, something like that. So after faster RCNN, then came these other set of methods like YOLO, which is called you only look once, and then single shot detector, where they thought, why do we need to do these two stages? Like, do we even need this extra RPN network? Maybe we can get rid of that also and directly use these feature maps and get predictions. So anyway, we have these features. Why can't we just use these features and directly get our classification and regression bounding box predictions? Why do we need another RPN network? So they basically get rid of this RPN network as well in the next model. So in YOLO, what they do is they take the input image, similar to what I just said, but rather than having a separate network, they use the image features only to predict the bounding box predictions. So they divide the image into a particular size grid, say S cross S. This is a hyperparameter which you can define. So in this case, what it's like a 7 cross 7 grid, right? 7 cross 7 grid. So and at each location they define these bounding boxes, something like this, where you can see right at each location there are so many boxes defined. So it is trained to predict two things. One is the bounding boxes, and the confidence. By confidence here it means the confidence is confidence of whether of an object existing in that particular box. Bounding box. So if it's of very low confidence, then you can just remove that box. And for each grid cell, it predicts a particular class. So this is like the class probability map. So here for these regions it is expected to predict what dog, and for these regions it's expected to predict cycle. For these regions it predicts background, something like that, background, road, these kind of things. So we have the total number of outputs is for the class probability map. So the grid size is S cross S set, and K is the number of anchors. That is, at each box how many anchors do I define. So anchors are basically these boxes which I define. So I do one like this, one of this aspect ratio, this aspect ratio, and so on. So I define like say some 5 anchors per location type. So K is the number of anchors which I define. C is the number of classes. So the final desired outputs is I have S cross S grid elements. At each position I want to predict 5 elements for a bounding box, that is 4 for location and 1 for confidence of whether a box whether an object exists or not. So this is called something like an objectness score or something, objectness score. So this has nothing to do with a class. It just says whether an object exists or not. Yes or no, binary classifier type. Plus C, this is for classification, right? So at each grid location, what class exists? I have say 10 classes, means I should get 10 predictions, right? 10 length vector. So that is for classification. So is this clear how the number of desired outputs are for YOLO? So YOLO, SSD, all of them follow a similar structure. Like it's like tiny details only are modified, but basically this is what they do. So what is done is we get the image feature map, right? So here these feature maps. So from this feature map, they define fully connected layers, FC layer, which will give out these many predictions. S cross what 5k plus C predictions. So these many outputs will come out of my FC layer, and what corresponds to what is kind of hard coded, like in the order which we give. So we use both of them are used to while testing. Both this and this are combined to get final detections. So this objectness score is there, right, which we get here from here. This confidence is used. So if this confidence is very low, then I'll ignore those boxes, which is how a lot of boxes will get rid of a lot of boxes. Then overlapping. So objectness score is thresholded. So a lot of these background boxes will get rid by this. After this you will do non-maximal suppression, so that redundant boxes you get rid of them. And once we do that, we get the class predictions from these. So you combine both this plus this to get these final detections in YOLO. Any doubts on this? Okay, so fine, yeah, YOLO was introduced. After this, there was this other method called single shot detector. So, what can be a drawbacks in this framework? With this kind of design, what kind of things can possibly fail in this framework, and how do you think it can be addressed? Dividing into grids. Yeah, maybe this number of boxes which I define can possibly not capture the whole spectrum of objects that can be present. There could be, it might not be able to identify small objects, or these bounding box can be erroneous and so on. Because I'm only dividing the image, like handling it in one scale, right? I'm not defining like small objects, large objects. I'm not really differentiating between them, so I might not be able to identify objects of different scale. So which is what the later paper, single shot detector, does. So what they do is, so in YOLO we get these final feature maps. From these feature maps I get do this, right? So final feature maps, usually, like the receptive field of this would be almost the whole image, right? So instead of taking the final features, they take all intermediate features and use intermediate features to do the to predict the bounding boxes and classifiers. Say if this is what, like if I use a VGG network in this, so it is a, yeah, 300, starting from a 300 cross 300 image, after passing it through this con layer, con fifth and 5, yeah, whatever, this element. So it has the spatial dimension is 38 cross 38. Then again it is downsampled to get 19 cross 19, 10 cross 10, 5 cross 5, 3 cross 3, and finally is 1 cross 1, right? So when if I use this 1 cross 1 feature, this can detect an object that captures the whole image, right? Like something like this. If the object is like this, then my final feature map can possibly give this. If my object is smaller like this, and like in this dog occupies only half the area of the image, right? So in such cases, earlier feature maps can be more informative. So the early layer feature maps can detect, so this can detect very small objects, these features. So as I go deeper into the network, so this would be like some medium scale objects, and here it would be large objects which cover the almost the whole image or something like that. So by using these multi-scale features, it handles objects at all scales. So here it is done, it's very similar to YOLO after this, just that features are extracted from different scales. So at each intermediate step they define the so we'll have this FC layer, right? These features are passed through an FC layer. So the classifier is of this dimension here. So 3. So this 3 cross 3 is like the grid size. There we had S cross S, right? Something like that. 4 is the number of anchors. This is the number of anchors. This is the number of classes. Plus 4, this 4 is for bounding box. Classification and bounding box. So this number of anchors can be, I mean, it's a heuristic. Just they've used 4 anchors here. At this scale they have used 6, and in the last they have used 4 anchors. So at the end they have 8732 bounding boxes. In selective search we had 2000 in all the previous ones they were predicting, right? So by doing so many at all scales, they predict in total 8732 8732 bounding boxes. Yeah, and once you get all these predictions for each box, you will get these class predictions and all, right? So then they pass it through non-maximal suppression to get rid of redundant bounding boxes. Yeah, so this is how the different scales will be handled. So suppose when I am using an 8 cross 8 feature map, this is how the anchor boxes would be at each grid location. So that these are the number of grid locations, right? 8 cross 8 feature map, and this will be how the anchor boxes will look like. So this matches with the scale of the cat here, right? Later when I have 4 cross 4 feature maps, so these are the anchor boxes here. So this scale would match the that of a dog. So while training, this get maps to these kind of boxes and they refine them. So this is how it can handle different scales. This is the same concept. So what is predicted for each of the box? I regress the bounding box, that is delta. This is the center location CXCY and WH. We predict how much this anchor should be shifted. So this box I would have to stretch it somewhat, right? Like stretch it something like this so that it fits the dog. So that is what gets predicted here. And this confidence is, so there are p class number of classes means whatever, yeah, c number of classes. So those many, this is the confidence scores that this particular box has this particular class. So while testing, what would happen, uh, this location would be predicted, the bounding box offset, and then the class we pick the one with the maximum score and associated with that class. Then by doing non-maximal suppression we get rid of the redundant boxes. So but then all these bounding boxes across all the feature maps are pulled together, so we'll have that 8.8732 bounding boxes. For each box we get 5 predictions, 5 predictions, this, which is then passed through non-maximal suppression, and then we might get a countable number of true objects detected. Yeah. Is this clear? What the difference between SSD and YOLO? Can you go over YOLO V3 and other variants? Oh. Extra feature layers? I didn't get your question. You can unmute yourself and ask. No, I just asked if you have any doubts with SST and your. Okay, I will. Yeah, let me. You can see my screen, right?
Yes, ma'am.
Okay. Yeah, I'm also not very sure of the YOLO variant, but the idea is very similar. I mean, how it went from YOLO to SSG addressing something like that. So let's see. Yeah, so in YOLO, okay, here they did not really have. They didn't really have anchors, but then at each location they would predict a certain number of bounding boxes and have a confidence score. But like directly predicting the bounding box locations is harder, like to exactly identify what the XYWH would be. So to address that, in YOLO V2 they define these anchor boxes, which is similar to what was done in that region proposal network, right? So they specifically at each location they define what is XYWH for each anchor box would be, so that in such case it can predict. Okay, what does it predict? It predicts 5 coordinates per anchor box, that is tx, ty, tw, th, and TO. The TO is that objectness score, whether an object is present in that or not. So it learns to predict the delta by which this box can be shifted. So these boxes are these are hard coded initially itself. That is, these many locations are there, that is cross S grid. At each location, 5 different boxes are hard coded. So that's the default boxes. How much should I shift them? That is what is predicted by the CNN. So this is what they do in YOLO V2, introducing anchors. In YOLO V3, what do they do? It uses logistic regression to predict objectness score for each bounding box, assigns only one anchor box to each ground truth. Okay, the main thing what they have done is the multi-scale thing in this. It looks like that is they've used this different architecture called darknet, and this is called spatial pyramid polling network, where so so they are like sort of imitating multi to extract multi-scale features from this final layer by having this special pyramid polling block. That is, so if I have so spatial pyramid polling is usually if you use different filter sizes and combine them, so that like if I have a 3 cross 3 filter, if I have a 5 cross 5 filter, 7 cross 7 filter, so I will the receptive field of those filters would be different, right? So what it imitates like looking at multi-scale features. So that is what spatial pyramid polling does. But this diagram is not clearly understandable. Okay. Yeah. So what is happening here is, so suppose my feature dimension is 13 cross 3, 13 cross 13. So they use different filter, yeah, I don't know if they're using convolutional filters or max pooling to do to bring down this 13 cross 13 feature maps to the dimension of 5 cross 5, 9 cross 9 and 13 cross 13 by doing something using different filter sizes. So from this I have downsampled and I've got 5 cross 5 filters. So this will basically look at big features, right? Like because I've condensed 13 cross 13 feature map to 5 cross 5. So that means each fixture here would look at a larger area in the image. Then there's 9 cross 9 and then there's 13 cross 13. So after they pull this, I think they do um, interpolation to bring it back to the same size, 13 cross 13, and then concatenate here. So here, so I will have some channels which have so some channels which will look at bigger objects, some channels which will look at mid-range object sizes, and some channels which will look at very tiny fine-grained objects. So rather, so in SSD what is done is they collect features from different like stages in the network, right? So instead of that, this SPP block is, I have the final feature map, but from the final feature map I'm looking at different receptive fields type. So sort of imitating the multi-scale thing in the final features. So did you get an idea of what the spatial pyramid pooling does?
Yes, ma'am.
Okay. Yeah, so this YOLO V3 and SSD at a high level, it does very similar things, just that, I mean, these are like engineering stuff. The idea is same, but implemented in different ways. Okay, this one I have never seen this picture ever. Module for better feature alignment. Okay, in this they've used some different architecture called CSP Darknet and bag of special incorporate spatial pyramid pooling and path aggregation network to combine features across scales. Add a modified spatial attention module for better feature alignment. Okay, I mean this is a lot of tricks which they have included here to make this better. Even I am not sure. Mosaic augmentation combines four images into one, improving the model's ability to detect objects outside their usual contact. Okay, this is interesting. So I think what this does is like, say if I have an image captured in an indoor environment, something that's captured in an outdoor environment, and so on. If I put them together, then it will look at, I mean, sort of unnatural images also, right? And if you train using such augmentations, so even if you put it in a very unusual environment, it will be able to detect objects. So that's what this does, I think. So how YOLO has evolved is, yeah, this was the first single stage detector that was proposed, where you divide the image into grid and directly predict bounding boxes and probabilities for that each grid location. Then, because absolutely predicting what the grid is hard, they introduce these anchor boxes so that you can predict the what shifts, how much the anchor boxes should be adjusted so that it matches the ground truth, I mean true object box. Then they introduced multi-scale string by using that SPP layers, or yeah, something like that. Okay, YOLO V4 V5, I think they've just dumped a lot of heuristics to make the model better. So what has gone from YOLO V1 V2 V3, at least these three are three logical steps done, which is also simultaneously done in that single shot detection in a slightly different manner. There are a lot more YOLO versions. YOLO is something that never ends. I think people, even now there are new versions coming out. If you have anything specific, I mean, idea wise, I can explain, but these details are all very tiny. Like, as long as you understand at a high level what is required and how these things have evolved, it should be good, I think. So is that fine? Like if you have any specific questions, maybe ask. But so yeah, the last part of this lecture was on, yeah, the problem image segmentation, right? So image segmentation is what pixel. What do we have? We get pixel wise predictions, where for each pixel we want to predict what class it belongs to. Like in this case, this pixel belongs to car, this is the road, building, and so on. And one other very important problem which people look into is medical image segmentation to like identify tumor regions or things like that. So most image segmentation usually uses this encoder decoder architecture, or and all these are also called as fully convolutional networks. So in when we are predicting, I mean doing segmentation, we want to have a prediction for every single pixel, right? Unlike classification, where I am trying to collate all the information at all regions to give out one prediction. So we do not have those constraints as like the final fully connected layer here. So we get rid of the fully connected layer and only use fully convolutional networks. uh, I think the very first in FCN, fully convolutional network, which was proposed, so this encoder part is usually taken from a pre-trained backbone, like the AlexNet, ImageNet pre-trained backbone, because it has already. I mean, so why do we use these pre-trained backbones? Even in object detection, this is like everything RCN and everything which we discussed. I mentioned that pre-trained backbones are used, right? The task is different. Earlier, ImageNet was trained for classification, but detection, segmentation are different tasks. What I'm trying to predict from the image is different. So why is pre-trained model used in all these tasks, but not? I mean, I might as well train completely from scratch, define any kind of architecture and all, right? So why is this preferred? Anyone? So have you heard of the term called transfer learning? It is difficult to set all the hyperparameters and build a model from scratch. Okay. I mean, I can choose same hyperparameters that was used in ImageNet, right? Use the same hyperparameters, but fine, I'll train from scratch. What is the advantage of using that pre-trained model? to a step it is similar. So to reduce tasks, yeah, yeah, sort of. So when we use a we can leverage the learning of the model, yeah, right. So this is all called what, transfer learning, fine tuning kind of terms are you might have heard. Have you heard of these terms? I think sir has discussed right earlier in some fine tuning. So when I say transfer learning, it is basically I'm transferring the knowledge from one task to another because they're still somewhat related. In both the images, I'm still trying to understand what is present in the image, right? So in a CNN, these early layers, especially like here, these kind of layers, the first half of the network, say, would all look at very low level features. It would identify, learn to recognize things like colors, textures, shapes, like lines, circles, blobs, all such low level features, right? So this part of the network usually captures this kind of features, which is common across all sorts of images, like in any natural images, right, irrespective of what my task is. So the later ones are usually uh, like task oriented features it would try to capture, but the early layers would be are usually generic, which I can use across tasks like object detection, segmentation, any images. So starting from a pre-trained model, basically a when I'm training for object detection, so it already starts, and I mean it leverages all this information which the pre-trained model can already extract. So what would happen usually is these last layers get fine-tuned to for the new task, but these early layers information is like taken for granted. I mean even these can get updated, but it takes much lesser time to train because I've already trained to see all of these, right? So it just uses that information. So that is why in general, even if you guys have to build an CNN to do a particular task, new task, not imagine it, right? Like you want to do some other disease classification or something like that, plant diseases are there, some agricultural data, satellite data, all such things. Even when you're building system, you can just take an imaginate pre-trained model, start from there rather than training it from scratch. One thing is we can't afford to have so much data to train all these features again using new data, which is like only like ImageNet is a huge data set, right? So using which it has already learned all these features. But if I use a new much smaller, say if I have just 1,000 images, I might not be able to learn all of this, which is why transfer learning is a norm. Basically anyone does anything, we when we say training, in more often than not uh, it is usually transfer learning only or fine tuning the model. Yeah, so we use a pre-trained image encoder, that is we just rip off that fully connected network, fully connected layer, the last layers which are meant for classification. I just get rid of them, but I use that earlier full all the CNN layers. So that will usually make the encoder. And so say my encoder, say this is some 5 cross 5 map, suppose 5 cross 5 map, and my image is a 100 cross 100, even more, usually it's 224 cross 224, but I want pixel predictions at each of these, right? So to do that, usually there is this decoder architecture. Decoder, sometimes they just upsample this 5 cross 5 to 100 cross 100, use a decoder, have some skip connections, all of them. But basically you have to bring back the whatever your feature map dimension is, the encoder's feature map dimension, back to the original image size. So that is the decoder. This is here I'm encoding the information present in the image. Here I'm trying to decode the information present in the image to give out at every pixel what is the prediction. So this is my final say this is my final feature map. uh, yeah, so here they've written, right? So what are these layers present in the decoder? One is the upsampling layer. That is, so I have this 5 cross 5. So from 5 cross 5 I want to make it 10 cross 10. So this feature map I pass it to an upsampling layer, I get the bigger feature map. Passing through it upsample layer, I get a bigger feature map, and so on. So I keep doing this. And in the last layer I'll have another softmax layer. So this will be a 1 cross 1 convolution. So why 1 cross 1 convolution? So all of these are not 1 cross 1, right? It would be 3 cross 3 convolution or something like that. But only in my last layer I will have a 1 cross 1 convolution. Why do I do that?
We want to predict a class label for each pixel.
We want to predict class label for each pixel. So when I'm doing 1 cross 1 convolution, at every location I'm looking at it, right? So at every location I'll look at the whole feature map and give out. So if there are C classes, so this will be like 1 cross 1 cross C, right? So I'll get C predictions for each location. So that will be my final output feature map, output prediction layer. Then yeah, so along with in this encoder decoder architecture, these things called skip connections are usually introduced. So what skip connections does is, so the same, so I'm sort of mirroring this, right? So how in the exact same way I have come down from the big feature map to small one, I'm trying to mirror that and keep upsampling them, right? So when I've upsampled this, I take my early layer like the encoder feature layers and I give that as input to the decoder layer here. So these features, the input from the encoder layer, are also passed on to the decoder through these skip connections. So why would this be helpful? When I'm going from this to this, I'm usually doing max pooling and trying to get the global information, right? But in uh, segmentation tasks, I want fine-grained information because I'm looking at every pixel. I just don't want to. It's not about telling that the image has a cat. I want to be able to predict at every pixel that is a cat. So I need fine-grained information, which is actually present in these layers, right? These early layers. So to leverage that, these early layers which have local features of the image, so that is also passed via to the decoder so that it can leverage this fine grained information and it would be useful to make final pixel wise predictions. Oh, and this last softmax layer, right? So suppose I have to predict C classes. This layer, this filter size would be C plus 1. C is for the number of classes and 1 is usually a background class. Even when an image is labeled, right, they would be labeled background. If you do not like, yeah, in this case maybe not. Like here it would be sky. But if there are objects which I don't care about, suppose I don't care about where the sky is if I am looking at the road, right? So in such cases, this is be just labeled as background. Here this would be labeled as background. So it is usually a C plus 1 classification task. It's VS Code for that, but yeah, a few questions we'll look at. So, which of the following statements correctly distinguishes between object detection, classification, segmentation, semantic segmentation, and instance segmentation? So, yeah, can you read through these statements and tell me which of them are correct? Is the first statement correct about object detection? No, yeah, the first statement is wrong. B and D are right. So, what does B say? Classification assigns a single label to the entire image, indicating the most prominent class. While object detection identifies and localizes multiple objects in an image by drawing bounding boxes around them, right? So, this defines classification and object detection. So, C and D talks about semantic segmentation and instance segmentation. Yeah, so D says in instance segmentation, the goal is to classify and differentiate each instance of an object. So, as the name says, instance segmentation, that is, so if I have like two dogs in the image, I want to identify each of them is a dog, but there are two different dogs. That is what instance segmentation does. Differentiate each instance of an object. But in semantic segmentation, I don't care about telling there are two different dogs. All I care is identifying that pixel as dog without distinguishing between the two instances. Is that clear? The difference between semantic and instance segmentation. Okay. Yeah, B and D are right. So you are given two bounding boxes within an image with these coordinates, bounding box A and bounding box B. So what is the intersection over union between these two bounding boxes? So one box is set say 2 comma 4, so this is 2 comma 4, and then bottom right corner of the box is 8 comma 10, say something like this. The box is your first box, and I have a second box which would say something like this. Here this location is 5 comma 6 top corner, bottom right corner this is 12 comma 14. Now I want to calculate intersection over union. So what is this? So this is B1 bounding box, this is B2. So the top part would be B1 intersection B2 over union B1 union B2. So this would be the intersection part, and this whole thing would be the union part, right? So can you tell me what the area of intersection I mean this, the numerator and denominator here? So what is the area of this box, the inside box? 12. 8 comma 10, no, this is. So 10 minus 6 is 4. 8 minus 5 is 3. Yeah, 12. And what about the union? So what is the area, I mean the total area? 92 minus 12. Huh? So 92 is basically area of B1 plus area of B2 minus B1 intersection B2, right? So okay, I'm not calculating, I'm assuming what you said is right. So this is 92, this is 12. So it would be 12 by 80. Is that right? Yeah, 12 and 80. So the IOU is 12 by 80. So are these two boxes overlapping significantly? No, right? Yeah. Usually an overlap of zero point 0.5 and above would represent significantly overlapping boxes. So in such cases, if the intersection is low, I will retain both boxes. Focal mass. What you discuss these things? Okay, which of these following statements is true here? It's about fast RCNN and faster RCNN. So what is the change that is done from fast RCNN to faster RCNN? Is the first statement true? Yes, right. From RCNN to fast RCNN, eliminating. No. So what is the change we did in RCNN to fast RCNN? It was to get rid of that multiple predictions, right? I mean, multiple passes through the network. So A is false because RCNN to fast RCNN, those 2000 in RCNN, 2000 bounding boxes, I mean 2000 patches were getting passed through the CNN. So we got rid of that step. That is, the whole image is passed through the image, I mean the CNN, and then from the feature maps and the bounding box proposals, I extract the sub feature maps and do ROI pooling. So, but the selective search part is still there in RCNN and fast RCNN, both of them. So the first statement is actually false. What about the second statement? Faster RCNN further improves fast RCNN by introducing a region proposal network that shares convolutional features with the detection network, making the object detection process end-to-end trainable. So is this statement true? Is this true? No. Why no?
Maybe it is not end-to-end trainable. That's the reason. We have to train the network three times in three different trainers.
Yeah, oh yeah, they have multiple stages. They do train it in different stages, but I can still back propagate through both of them together, right? I think in the last stage they train all of them together, don't they? I don't remember exactly. But anyway, yeah, this is where they introduce RPN to get rid of selective search. It if I have to, this is end-to-end trainable because I can use the classification loss, box prediction loss, and back propagate through both of them. Okay, what about the third statement? Third one.
Now I returned that why it is end-to-end network.
Okay, let's just ignore that part. It is not a properly meant for. Uh, it I know they do train it in different stages. That is, they first train the RPN, then they train the CNN, then they do it together or something like that. But my point is, so I have an image, I pass it through this, I can pass the feature maps through RPN. I At the end I have two losses for classification bounding box. I can back propagate this through the RPN network and the feature maps to do training, right? It is a possibility, although it is not done. That's what I'm trying to say.
That's all.
I mean, because this is a new network, that first they do train it separately in stages. I understand that. But it can be end-to-end trained. I mean, so suppose you have trained this whole network for some cat dog classifier, cat dog, some animal. Suppose you have this whole framework. Now I ask you to do bounding box classification. I mean, for some other objects like vehicles or something. It's a new data set, and but I already have a faster RCNN which is trained. In such cases, maybe I can assume that this RPN is already doing a reasonably good job. I can fine tune in such case in an end-to-end manner if I have to. What? That is what I tried to say. So anyway, that statement is not well made. But you understood what I'm meaning, right?
Yes, ma'am.
So what is done is fine. It's multi-stage, but it's a design choice, right? How I want to train. If need be, I can do it. Uh, so is C true? Is in faster RCNN, the region proposal network generates object proposals directly from the raw input image without using any convolutional features, leading to faster and more accurate predictions. Is this true?
Mm.
No, right? It does use the convolutional features to give the predictions, bounding box predictions. So this is true, this is false. And what about the last line? Both fast RCN and faster RCN use a sliding window approach to generate region proposals. But faster RCNN's RPN generates higher quality proposals, reducing the overall computation time. Is this true? Is this true? I never mentioned the word sliding window in the whole of today, I think, whole lecture. It can't be true, right? I'm not using any sliding window approach in anywhere, in any of these methods. In fast RCNN, I use what? Selective search. And in faster RCNN, we use RPN. But I don't use sliding window in any of them. So this statement is false, right? So which of these statements describes key characteristics and functionalities of UNet model? First statement, UNet model is characterized by its use of a fully connected layer at the end of the network, which ensures that the entire image is classified as a single label. Is this true? No. Yeah, first one is not true. What about the second one? The UNet model uses an encoder decoder structure where encoders downsamples the input image to capture context and decoder upsamples it to produce a pixel wise segmentation map with skip connections that combine high resolution features from the encoder with the upsampled output. This is true, right? This is exactly what UNet means. What about the third one? UNet relies solely on convolutional layers without any pooling operations, making it highly suitable for tasks where preserving spatial resolution is critical. Is this true? No, right? In the encoder part, we do have pooling layers. So, what about the last option? In UNet architecture, skip connections are used to merge the output of the decoder with the input image, allowing the model to directly compare the original input with the final segmented output. Is this true? No, right? It's not used for that purpose. I'm not really comparing my prediction with input. My predictions are in the classification space, right? That is which class it is. It is not compared with my input image. So when is a case where this would be done, that say the decoder's output compared with the original input? Is there any task where such thing would be done? I give the input, I pass it through a network, I get an output, I compare it with my input only. In that case, what am I doing? I'm trying to create my input again from my, like recreate my input by passing through a network. Is such uh, image reconstruction, right? So in image reconstruction, that's what we do, right? Pass it, so encode the image, decode the image, compare it with my image itself. Yeah, B is the answer. Okay, so I'll quickly go over this notebook here. This is on segmentation, where they synthetically create a segmentation data set and define a unit, I think. and train it. So here we have the imports, and like, so there are some functions here that is to plot the image and so on. So here a synthetic data set is generated, which will look something like this. So so what is the task here? I think it is yeah, what kind of shape this is, right? So this is triangle, this is square, this is an octagon, I think, square, yeah, these things, right? So each of them are labeled differently. That is the color you see, right? Why is it red? Oh, so this is not really a full square. Anyway, so this is like a shape classifier, right? Um, it has to predict all these by colors, and this part like is the background, the white region. So that is what is the task. So here the data loader is prepared. The yeah, that data set is simulated, and like we have 2000 samples for training and 200 samples for validating. So this is how the training, I mean, a new sample would look like, and I would want to predict what these pixels are. That's an image, sample input image. Now here a unit model is defined. Let's look at the architecture. So here they have taken, they built a unit on a ResNet model. So their base model is a ResNet 18. So this is the encoder which they've taken, which, and they've loaded the pre-trained model, right? Pre-trained, this will load ImageNet pre-trained ResNet 18 model, and then so this function will list all the layers in the network. Base model dot children will list all the layers in sequence. Okay, so from that they define these layers, uh, the first three layers, and then which is followed by convolution and ReLU and so on. So this part will comprise the encoder, and then they upsample. This is the upsampling layer, and here they have some upconvolutional layers which will comprise the decoder part. So when you have an new input, uh, okay, I don't know why these two steps are there here, but yeah, here the input is passed here. So this part will all do the encoding part, and then these are the upconvolutional layers, the new layers which are defined. Upconvolution, I mean convolution, then there is upsampling layer, then again a convolution, and this concatenation is the this is the skip connection basically. So this layer 3, this layer is concatenated here, and you do upsampling, then the layer 2 output. So this one is layer 3, then the layer 2 output is concatenated here, then you do upconvolution, upsample, then the layer 1 output here is concatenated here. Similarly we do this whole thing, and this last layer will be the classification layer. So this conv last will comprise of con last is the number of classes, right? So 64 is the number of channels and n class is the number of classes. So that is the definition. Here we instantiate, like call, create an instance of that class. So these are 6 classes. I think there were 6 shapes in that, I think. So this is how the model architecture would look like. Yeah, it has some convolution max pool layer. Then like these are the ResNet blocks, which are like defined as layer 1, layer 2, which is a sequence of CNN, I mean convolutional layers anyway. So these are the ResNet blocks, and then from here the upconvolution, I mean so these are the decoder layers. This shows what is the output shape after passing through each layer. So this, you can use this function called summary. So this is the model definition. So this is the input size, right? This is what the image dimension which I would be passing. So if I pass this sized image dimension, what would be the output shape of each after each layer? That is what this shows. So here you can see 224 cross 224, there are 64 channels, it gives out the first layer. Then there's one, I think after this there's probably, yeah, max pool layer don't show up here, but yeah, after this I think there's a max pool layer, that's why it would become 112 cost 112, then 56 dimension, then it becomes 28 cross 28, then 14 cross 14, then 7 cross 7. So from 7 cross 7, this is that bottleneck part. After this it starts, like the decoder part starts. So this is upsampled to 14 cross 14, then upsampled to 28 cross 28, then 56 cross 56, then 112 cross 112, and finally 224 cross 224. 224 cross 224, and then this 6 is the number of classes, the last conv layer, no? For the softmax, this is the softmax layer. Yeah, and it defines the total number of parameters, trainable parameters, everything here. So here the loss function is defined, and yeah, here the main training loop is there. So we have passed the model, optimizer, scheduler, yeah, data loaders are global here, I think. So yeah, you loop over the number of epochs. So this whole thing will be similar to what we did in classification. So there's the training phase, validation phase, and first you're training it, so this is one epoch, so it iterate over the whole data loader for the training data loader. And so if it is training phase, then you optimize it. So yeah, I mean the loss all is pretty much this structure will remain the same, but these outputs and labels will be in what dimension? It will be in 224 cross 224 dimension. It's not it's not like classification, the dimensions would be different though. So here, yeah, this is where the training part is done. We define the model, then freeze backbone layers. So these layers, the early layers, the encoder layers, need not really be trained. So you can freeze those backbone layers and only to learn the new layers, decoder layers. These also can be fine-tuned, but it's not necessary that you fine-tune them always. So this is how you can freeze some layers in the network. Suppose I don't want to train, here it considers all base layers, that is all encoder layers, but sometimes maybe the first 3 layers I will freeze, the last few parts even in the encoder I can keep it trained. So I can choose which parameters I can set as trainable or not based on this. Then this optimizer I define based on like whether it requires gradient or not. Based on that it will collect all the model parameters. and define a scheduler and pass it to this train model. So that is like a basic overview of what is how a segmentation model is trained. Let's just print these shapes. So here you can see, right, it is, so 25 is the batch size and the outputs predicted is 6 comma 192 comma 192. So 192 comma 192 is the image dimension used here, and 6 is the number of classes. So the labels are also in the is of the same shape. So these labels are like one hot vectors, that is why this is 6 here. So it will have 1 at only one of the 6 positions. In classification we'll usually have just one number, right? It will not be like 6 classes doesn't mean one hot. It depends on the function exactly you're using, but yeah. Okay, so while prediction you just pass the inputs to the model, and so this is a very simple task, right? As in understanding these shapes, like real data sets would be much harder to train and all that. But the trick is usually to do transfer learning. Take the base network which is already trained and you can fine tune with like even a few hundreds of images. But you can't really train a good segmentation model from scratch. If you have say 500 images, that might not suffice. But if you start from a pre-trained model, then you can use it to fine tune it for simple tasks at least. Okay then, yeah, that's all. We can end the session here. Thank you everyone for attending. Thank you.